Hello, everyone. We're in our last unit of the course, Electricity and Magnetism. So one of the things that we're going to do in this unit is we're going to review a little bit of stuff that you learned back in grade 9 science, and possibly before then, and see how these two seemingly very disconnected things, electricity and magnetism, are actually very closely connected. So let's start with electricity, which in your textbook is in chapter 12. So the first thing we're going to look at are electrostatics. So this word, electrostatics, comes from the idea that we're looking at something where we have electrical charge, or something that's charged, and the static means that there's nothing moving. Okay. The first thing to remember from before is that there are two kinds of charges: positive charges and negative charges. And there's a fundamental law of electric charges, which is usually attributed to Gauss. And that says that like charges repel, but unlike charges or opposite charges attract. So this little diagram basically shows how this goes. If you have a positive charge and a negative charge, they will attract one another. But if you have two positive charges or two negative charges, they will repel each other. Okay, so now this gets into the next concept, which is electric fields. It turns out, now we spend more time on this, much more time on this in grade 12 physics. So in grade 11 physics, we just need to know a little bit about this. And all you need to understand for grade 11 physics is that around a charge, there are electric field lines. And those lines are drawn in such a way that they tell you what a positive charge would do. So the idea is around any given charge, there is a space, and in that space, there are these electric field lines that will either attract or repel other electrically charged objects. So in the case of single charges, this is how the field looks. It's radially outward in the case of a positive charge, because if you think about it, any positive charge would repel from that positive charge and it would want to go away. However, in the case of a negative charge, it's radially inward, because again, the same idea. If you had a positive charge near to that negative charge, it would want to go inward. It would be attracted to that negative charge. So this is really all we need to know about electric fields, is that the shape of them in the case of single charges is radially outward in the case of the positive charge, or radially inward in the case of the negative charge. Things get a little bit more interesting when you have two charges. So the diagram on the left is a classic dipole, where you have a positive charge and a negative charge. So in this case, the electric field lines point from the positive charge towards the negative charge. So that's what those arrows are indicating, right? Which way would a positive charge go? Well, if the positive charge were near to the blue positive charge, it would want to repel. It would want to get away. And at the same time, any positive charges that were near the negative charge would want to go into the negative charge. They would be attracted. So that's why those field lines are drawn that way. However, different story if we have two like charges. And so the way I've drawn it in the case on the right is two positive charges. So two positive charges, the electric field lines are sort of radially outward. However, in the middle, down the middle there's this place where there's no field lines, and that's called the nodal plane. You might remember that word node from when we talked about waves, but that line is that line that goes in between them, where there are no field lines. That's essentially where there is no electric field. So a charge placed perfectly in the center would not move at all. It wouldn't be attracted, or, well, in this case, it wouldn't be repelled, because it's kind of balanced in between the two of them. So it would experience no net force. Okay. So we have these charges, positive charges and negative charges. And it's a reasonable question to ask if we can have any amount of charge that we want. We can certainly have a lot of charge, but what's the smallest amount of charge that we can possibly have? This is actually the elementary charge. So the unit of charge is the coulomb, or capital C. And the symbol for an elementary charge, the smallest amount of charge that you can have, is the lowercase letter e. And this is actually the amount of charge that exists on either one proton or one electron. This is the number, 1.60 times 10 to the negative 19 coulombs. That's the smallest amount of charge that you can have on anything. You can't have less charge than that. So you may know that an electron is negatively charged and a proton is positively charged. So that immediately gives you the sign, positive or negative, that you would get if you had more of these things, right? So if you had a collection of protons, collection of positive charges, you would have a large positive charge. If you had a large amount of electrons, you would have a large negative charge. So since the basic building block of charge is the elementary charge, anytime we have more than that, anytime we have more than the elementary charge, then there's we can't just have we can certainly have one elementary charge, we can have two elementary charges and three, but we can't have fractional charges. We can't have like 1.5 electric charges. So as a consequence, we always know that however much charge we have, it's got to be divisible by the elementary charge. Or to put it another way, the amount of charge that we have is always some integer number of elementary charges. So in the equation here, Q is the total charge on our object, N is some integer, and E is the elementary charge. Okay, now we come to the last thing in this video, and that is the concept of electric current. This one will turn out to be quite important for your lab this week. I started with the idea of electrostatics, and in that case we had charges that weren't moving. An electric current implies that there's some kind of motion. So kind of like the current of a body of water, like a river or a stream. However, in this case, the thing that's moving is actually the electric charge. So in this case, we have electric charge moving through a conductor. And current is therefore the amount of charge that passes through the conductor in a second. So that's the definition. And that gives us a nice equation here that I, which is the current, the electric current, is equal to the total amount of charge, Q, which we just talked about, divided by the amount of time. The unit, by the way, for current is the ampere, or amps for short. And the unit for charge is the coulomb, capital C, I already mentioned that, and of course the unit of time is the second, the usual unit that we've used all through the course. Now current is a little bit tricky because depending on who you ask, current can flow in one of two possible directions. So the first one that I'm going to talk about is what's known as conventional current, or sometimes called electric current. And this is the preferred direction when we use physics. This is so the two methods, this one, conventional current, and the one that I'm going to talk about in a moment, they really only differ in terms of their direction, at least as far as this course is concerned. But later on, when you start talking about these things more mathematically, then conventional current is preferred because, well, without getting too deeply into the details, it keeps all of your numbers positive. Whereas if you worry about the other kind of current, which is called electron flow, then you have negatives lurking around. Conventional current is typically used by scientists, and the other kind of current, electron flow, is more typically used by engineers. So bear that in mind when I go through this. Anyway, back to a conventional current. So when we talk about electric charges, we're usually going to be talking about them in terms of a circuit. And part of that circuit is the battery. And the battery has two terminals, the negative terminal and the positive terminal. In conventional current, we say that electric charges move from the positive terminal to the negative terminal. That's basically the deal. So in this diagram, you can see that I have my battery with the two terminals, positive and negative, and the electron flow is going from the positive terminal to the negative terminal. In the case of electron flow, the direction of the current is reversed. So everything about this diagram is the same except the direction of the flow. So we're saying that electrons travel from the negative terminal, through in this case, the light bulb, and then to the positive terminal of the battery. So again, in terms of the actual understanding, it's not really that much difference. But for our purposes, we use conventional current, the first one, because it makes our lives in terms of the math more easy. It's really a choice of convenience as opposed to necessarily an understanding. Okay, so let's just go through this sample problem. A light bulb with a current of 0.75 amps is left on for 35 minutes. How much electric charge passes through the bulb? Okay, so how much electric charge passes through the bulb? In other words, electric charge, if you'll remember, is Q, capital Q. And my current, 0.75 amps, that's capital I. And my time, delta T, is 35 minutes. So we want to know how much electric charge passes through the bulb. Why don't you pause the video and try and work that out? Okay. So let's look at this problem. I've gone ahead and written down the information that we were given, our current, our time, and the thing that we're required to find, which is in this case our charge. So I want to go back and use the equation that I introduced a moment ago, that definitional equation. Current equals charge over time. Okay, there we go. All right, so in order to solve for Q, I'm going to multiply both sides by delta T to get Q equals I delta T. Now, this looks like a simple matter of just plugging in the numbers, but keep in mind that my time has to be in seconds. But right now you can see it's in minutes. So as a consequence, I have to take care of that with a unit conversion. Q equals, the current is fine, 0.75 amps, that's all good. But my time, I have to convert to seconds. So for that, I need to know how many seconds are in a minute, because I have 35 minutes, but I'm going to multiply that by 60 seconds per minute. Okay, and close up that. And now I see that my units are going to divide out. Minutes will divide with minutes, just like that. All right, and now the units that I have left are amps and seconds, and those two things, when they multiply together, give me the coulombs that I need. So the rest of this is just a matter of straight up plugging and chugging into my calculator. Okay, so you can do that, I'm sure. Just multiply 0.75 times 35 times 60, and you'll get your answer. Oops. Okay, so hopefully when you put that into your calculator, you got 1.6 times 10 to the 3 coulombs. And that's it. Okay, so in this lesson, we basically talked about, I just reviewed the law of the principle of electric charges, talked very briefly about electric fields produced by different kinds of charges, talked about the elementary charge, and how to connect charge and current. Now that principle, that concept of current is going to become very important in the next lesson, because in the next lesson we're going to talk about electric circuits, which is part of your lab for this week. Okay, see you then.